Good afternoon, ladies and gentlemen. In this short video, we're going to do the practice problems for practice A and B in chapter 18. So we're in circuits and circuit elements. Okay, so the first one is number 16. The question is, a length of wire is cut into 5 equal pieces. If the piece has a resistance of 0.15 ohms, what is the resistance of the original length of the wire? So it tells you what the resistance is of 1/5 of the whole length. I want to draw your attention to the worksheet that I provided for you guys for chapter 16, 17, and 18. On the back side, we already talked a little bit about current being charged over time, charge passing. And so I'm going to bring down to the lower part here where we have change in potential or voltage is current times resistance. All right, and I want to come down here to the resistors in series and the resistors in parallel, because these homework problems are going to be having us work with resistors in series and resistors in parallel. So resistors in series, what is the total resistance? You have R1 in series with R2. The total resistance is just R1 plus R2. So if R1 is 100 ohms and R2 is 200 ohms, then you'd have 100 plus 200, so you'd have 300 ohms. And if I took my multimeter and did it across this node and this node, top here and the bottom here, put one lead here, one lead here, I would read 300 ohms. And what happens if they're in parallel? Parallel is different. Parallel, hopefully this is going to look familiar to you from when we did lenses. Here we're going to discover that the total resistance, the inverse of the total resistance, is equal to the inverse of each of the resistors that are in parallel. So here, interestingly enough, if the first one is 100 ohms and the second one is also 100 ohms, then 1 over R total will be 1 over 100 plus 1 over 100, which is 2 over 100. So therefore, our total is 100 over 2. We have to take the inverse. 100 over 2 is 50 ohms. So if I have 100 ohms parallel to 100 ohms, my total resistance will be 50 ohms. So it turns out if they're both the same, then your total is going to be half. All right. So let's start with the first problem. First problem is here, number 16. It says a length of wire is cut into 5 equal pieces, and each piece has a resistance of 0.15 ohms. What's the resistance of the total length wire? So I went ahead and tried to draw that. Draw that right here. So I have one length of wire here, and I divided it up into 5 equal pieces. And it told me that, and this is number 16, it told me that the resistance of one of the pieces is 0.15 ohms. So I can say here that the resistance of the length of wire of 1/5 of it, so the resistance of length of wire, but a fifth of it, a fifth of the length of the wire is 0.15 ohms. So that means this one's 0.15 ohms, and this is 0.15 ohms, and this is 0.15 ohms, and this is 0.15 ohms. And you can imagine them as attached, because they are, so they're in series. So we're just going to add them all up, or just say that the total here is going to be 5 times 0.15 ohms, because this is for each one. So what is that? I take 5 times 0.15, and I get 0.75. So I have 0.75 ohms. Remember, ohms is actually omega, and that is the units for resistance. So that's it. That's my total resistance. All right, let's go to the next one. Now we have some more fun here. If you have a 4 ohm resistor and an 8 ohm resistor and a 12 ohm resistor that are connected in series with a 24 volt battery, then determine the equivalent resistance for the circuit and the current. Now, I already told you these are in series. I believe it's easier to visualize it, so I drew it out. So here's what I came up with. I drew 3 resistors in series to each other, and it's in series to each other to a battery. So here's my representative of a battery or a voltage source, power supply, and I have R1, R2, R3 in series. Now, what does it mean in series? It means that they each are sharing a node. So between R1 and R2, there's one node that they share, only one, because this one is connected to the negative terminal of the power supply, and The other side of R2 is connected to R3. So R1 is in series with R2, and R2 is in series with R3. They each share a node. Okay, so let's see what it is. R1 is 4 ohms, R2 is 8 ohms, and R3 is 12 ohms. And if you look at your reminder sheet, oh, that's right. When they're in series, all I have to do is add them up. That's all I have to do. So R1, R2, R3 are in series. I'm going to write here in series. So therefore, I'm going to add them up. What's R1 plus R2 plus R3? That's going to be the R total. Okay, the total. So I'm going to add 4 plus 8 plus 12. So 4 plus 8 plus 12. Let's see. 4 plus 8 is 12, plus 12 is 24. So I'm going to have 24 ohms. So that's my total resistance. Okay, so our equivalent is 24 ohms. All right, that's supposed to be a 2. 24 ohms. Next question, what is the current? How much current is going around in this circuit? Okay, so we have a closed circuit here. We have a current going through here, here, all the way around and through all those resistors. All right, so I'm going to just sort of show here that we have current, and we use the symbol I for current. Okay, current. So I happen to have memorized V equals IR. That's the only one I have memorized. V equals IR, and then all different versions. But I want I. I got the V, and now I have the equivalent. The equivalent. So I'm going to say here equivalent. This is the equivalent. All right, so what is the current? Well, I'm going to divide R equivalent to both sides, and I get the voltage divided by the equivalent resistance. That's the current. All right, so what do I have here? I have 24 volts, and my equivalent resistance is 24 ohms. Don't need my calculator for that. 24 over 24, and I have 1 amp. 1 amp. Let's see, I guess we have two significant figures, so I'll put 1.0 amps. So 1.0 amps. So that's what I have here. I have 1.0 amps. That's my current. All right, so that was all we had to do was take a look at what they're asking for and draw a picture. It's always easier to draw a picture. Okay, so that's all we have for practice A. Let's look at the practice B. First problem. Seems kind of similar. All right, it says number 18. The resistors in item 17, oh, the same ones from up here, the 8, the 12, the 4, 8, and 12. It says they're connected in parallel across a 24-volt battery. Now notice how it says the word across. That's important. And we want to know what's the equivalent resistance for the circuit and what's the current delivered by the battery. Current delivered by the battery. So we're going to draw a picture. All right, I'm going to write here. Now we're on prep for practice B, and I believe it's the same page, page 667. Okay, so we've got 4 ohms, 8 ohms, and 12 ohms, but this time they're in parallel. Oh, I think I drew this picture already. I did. I already drawn the picture for you here. All right, so here we go. I drew 4 ohms, 8 ohms, and 12 ohms all in parallel. So what does parallel mean? In series, they only shared one node. Here, they shared 2. What do I mean by that? Between the 4 ohm and the 8 ohm, you can see how they're connected to each other. So I actually could draw them like so. Let's see, I'm going to try to draw like this. Here's one resistor. I'm going to draw the other resistor. And I'm going to draw the other resistor like so. And I'm going to draw the power supply, the battery. Now they're all sharing the same node. But that's not how we draw circuits. We draw them in nice little square boxes. Makes it easier for analyzing the current, the voltage drop, etc. But I want you to see how they're all sharing the same node. And why is that? Well, we're going to say that there's no resistance on a just plain straight wire. So if that's the case, then this node and this node is the same as this node is the same as this node. Okay, they're all connected in parallel like so. All right, so what do we know about parallel resistors? Looking at your review sheet, oh, this is the one where the total resistance, it's the inverse of the total resistance, is equal to the sum of the inverses of each of the resistors. So let's look at that over here. So if I'm looking at this picture here, I know that the inverse of the total resistor is going to be the inverse of the first one plus the inverse of the second one plus the inverse of the third one. So we need to add this up, and that'll give us the inverse of the total resistor. Okay, so let's see with my calculator. I use a calculator here. Okay, 1 and 12. Here we go. Clear? Let's do the inverse of 4 plus the inverse of 8 plus the inverse of 12. And I get 11 divided by 24. So the 1 over our total is 11 over 24. Okay, so therefore our total over 1, I'm just going to flip it around. Our total, this is our total over 1, is just our total. Resistance total is 24 divided by 11. Okay, now I want the reciprocal. So I'm going to say, give me the reciprocal. Oh, I already did that. 24 out of 11. Okay, so the reciprocal is 24 out of 11. Yeah, 24 out of 11. I knew that, but tell me what that is. So I have to hit this button here. There it is, 2.18.18.18, repeating. So the total resistance is 2.18.18, etc. ohms. So there's my total resistance. So we could round that up to 2.2. 2.2 ohms. So what that means that this voltage source, this battery, the battery doesn't know how many resistors are connected to it. The battery doesn't care. So that you could actually imagine the battery just hooked up to one resistor, also known as an impedance, and it's 2.2 ohms. Okay, so what does this mean? When we say across, it means if I were to take the leads from my multimeter, put one here and here, one here and one here, I would get 24 volts. Here and here, I'd get 24 volts. I get here and here, they get 24 volts. And of course, here and here, I'd get 24 volts. So I have 24 volts, and it looks like there's just a resistor of 2.2. The equivalent resistance 2.2 ohms. That's supposed to be an omega ohms. Okay, so the question is, how much current is going through this? What is the current that's going around in this circuit right here? According to the one that's going through the battery. Okay, so I know that the voltage is equal to the current times the equivalent resistance. I got my equivalent resistance, I got my voltage, so let's solve for the current. So the current is just the voltage divided by our equivalent. I divided our equivalent to both sides. Our equivalent cancels out here. So I have current is voltage over our equivalent, so I have 24 volts divided by 2.2 ohms. All right, let's see what that is. Actually, you know, I'm going to leave this here. I'm going to ask for the inverse of that. The inverse of that times 24. The more accurate, right? Comes out exactly 11. Exactly 11 amps. So I have 11 amps. And if you had rounded off, what would we get? We get 24 divided by 2.2. And this is exactly why I like you guys to try to keep your numbers as accurate as possible by not rounding off to the very, very end. So you would see 10.9, oh yeah, that's about 11. When actually it's exactly 11. All right, so we have 11 amps in this situation here. Now let's compare it with the previous problem. Oops, I think I didn't tear out the page. Let me tear out the page. All right, so we can compare here, to unzoom here. Okay, so in the series case, we added them up, and then V over R equivalent is the current. I end up with 1 amp, and it's just 1 amp. But if they're in parallel, big difference. If they're in parallel, I have 11 amps. That's huge. Remember, it's in the milliamps that can kill you. So that's a lot of current. So it turns out the more you keep stringing along on here, you're going to get a smaller and smaller equivalent resistance. And the smaller your denominator here, the bigger your current's going to be. Okay, so I really want you to think about that because that's the big takeaway here. When you have it in series, you're going to be increasing your equivalent resistance. And if I keep increasing the denominator, then that's going to make the current smaller. But when I have them in parallel, the opposite happens. My equivalent resistance is going to get smaller and smaller and smaller and smaller, and then smaller and smaller and smaller, I'm going to have a larger current. And this is what happens when you plug too many things in at home and you blow the circuit, because it wants to protect the circuit breaker is going to open that circuit so that your house doesn't get burnt down because you're trying to drive too much current. Okay, because everything you plug in, they're all connected in parallel. All right, let's do the last problem. The last problem says, give me my pen here, an 18 ohm resistor, a 9 ohm resistor, and a 6 ohm resistor are connected in parallel across a 12-volt battery. What is the equivalent resistance for the circuit, and what's the current delivered by the battery? All right, so we'll pick this paper here. So this was number 19. So again, I'm going to draw my resistors in parallel. They're kind of these angled things. All right, so there's my 3 resistors, and they're all connected in parallel to a power supply or a battery, which is, what does it say here? 12 volts. I have 12 volts here. 12 volts, and I have 18, bring it down so you can see it, 18 ohms. So this one's going to be 18 ohms, this one's 9 ohms, and this one is 6 ohms. So it wants to know what is the equivalent resistance and what is the current from the battery. Okay, so we're going to draw, the current goes from the plus to the minus. So what is I? The current that's coming by the battery, current delivered by the battery. So I'm going to go this way. If it goes this way, then the current goes that way. All right, so let's do this again. We got these things in parallel. Another way to represent that is say 18 ohms is in parallel with 9 ohms, which is in parallel with 6 ohms. So if they're all parallel to each other, I know that the equivalent resistance, or rather the inverse of the equivalent resistance, is 1 over 18 plus 1 over 9 plus 1 over 6. All right, in this case, I'm not going to use my calculator. Why? Because I know that if I put 18, they all have the same common denominator as 18, right? So let's see. This one is 1 over 18. This one is 2, right? 2 18s is 1/9. And this one would be 3, right? Because 3 times 6 is 18. I always avoid my calculator because I trust my addition more. 1 plus 2 is 3. 3 plus 3 is 6. There's 6 over 18. All right, so 1 over the equivalent resistance is 6 over 18. So the equivalent resistance is 18 over 6. 18 over 6, which is 3 ohms. Now notice that when you are trying to figure out the equivalent resistance of a bunch of resistors that are in parallel, you're always going to end up something smaller than your smallest one. Here, 18, 9, and 6. 6 is the smallest one, and you end up with something smaller than 6. All right, let's say you didn't believe my math because you want to use your calculator instead. So let's do 18 inverse plus 9 inverse plus 6 inverse. There we go. And obviously the inverse of that is just 3, which is what we came up with, 3 ohms. All right, so there's our equivalent resistance. So the power supply just sees a 3 ohm resistor. That's all it sees. So you can call this equivalent circuit. That's all it sees. So I want to know how much current is going delivered by the power supply. Right here, it's going round and round. Okay, so V equals IR. The only thing I've memorized, this is equivalent. So my current, therefore the current is the voltage. I'm dividing our equivalent to both sides. So I have 12 volts divided by, I came up with 3 ohms was my equivalent resistance. This is 3 ohms. And so 12 divided by 3 ohms. And what I end up with, 12 divided by 3 is 4 amps. 4 amps. That's a lot of current. 4 amps. All right, one of the things you're going to learn about later, I'll just briefly touch on, is now that you know that 4 amps are coming from the power supply, now you can figure out how much current goes to the 6 ohms and how much current goes to the 9 ohms and how much current goes to the 18 ohms. When they come through that, then they collect again, they add up, the currents add up, and it will be 4 amps. when they come together again. So we'll probably do that next time. All right, so again, in parallel, it means that across this resistor here, I have 12 volts. So I take my leads, my red and my black on my multimeter, and I'm going to measure 12 volts between this across this resistor, across this resistor, across this resistor, and obviously across the battery. And that's what it means by being in parallel. Okay, not so when it's in series. Different story. Here, the voltage across this resistor plus the voltage across this resistor plus the voltage across this resistor is equal to 24 volts. But the current is the same going through the whole circuit. It's the same, the current. Okay, and basically, because V is equal to IR, you're just going to take that current and multiply it by the R. So if the current here is 1 amp, I multiply it by 4. I know I got 4 volts across here. So I'm going to write that down. So I got 4 volts across that resistor. Here I've got 8. 8 times 1. Oh, I've got 8 volts here across that resistor. And here I've got 12. So 12 times 1, I have 12 volts. And it turns out that 4 plus 8 is 12, plus 12 is 24, sure enough. So the voltages here add up all the way around to the power supply. All right, so a big difference between parallel and in series. Here you go. If they're in series, to get the equivalent resistance, you just add them up. And if they're in parallel, the inverse of the total resistance is equal to the sum of the inverses of all the other resistors that are in parallel. And that's all I have for you. And I can't find my mouse. Here it is. So I'll see you next time. All right. Adios.